just before you went out to the break was, is this actually a norm space? Did any of you think about in the break? Of course, you are not forced to, but if any of you got an idea, I would like to hear it. So let's do the same as I did just before the break. We discussed the space L1, and I say, on this space we would like to make a norm. That means to each element in the space we need to associate a real number. So not something that could be infinite, it should be a real number. And then we say, but the space is defined exactly as the set of sequences for which this is finite. So that means a natural choice for the norm would be to say, why don't we take this as a norm? As you could see here, this actually works, and this is what you will prove today at the problem session, that this actually goes without any problems. If you do exactly the same here, you would say, now we're looking at some sequences for which this is finite. So the same philosophy should say, let's try to take this as the norm. Now you can already hear on the way I say it, it will not be that easy, but the first guess for our norm would be to try to put the norm of xk, k equal to 1 to infinity, put this equal to the sum of xk to the power p, k equal to 1 to infinity. So can any of you tell me why does this not work? So if you look at these conditions to a norm, there's one of them that will give you a problem right away. Dario?
It doesn't satisfy the second condition.
You had a problem with the second condition. Because if you look at the norm of, and then instead of taking the sequence, we multiply with some alpha. That means we look at alpha and then xk, k going from 1 to infinity. Then this would be the same as to put the alpha here, so we get the sum k equal to 1 to infinity, and then we get alpha xk to the power p. And the way you have to manipulate with this is to say this is the absolute value of alpha times the absolute value of xk, each of them to the power p. That means the alpha will go out as alpha in absolute value to the power p. So what comes out here would be alpha to the power p times the norm of xk. And what we would like is that it just comes out as the absolute value of the alpha. So usually people say, never write anything on the board which is wrong. And this is what we just did, because I wrote down something that was just a guess. It turns out not to be correct, that you can see this is not correct, because we would like it to be the same as just alpha times the norm of xk. So what I could do is just to cross it like this. I mean, the calculations are okay. They just show us that this is not the right choice for the norm. So we make another guess. So you might look at what we did, and you might ask, how can we modify it to take care of the problem? And you see, the problem is that with the definition we had, the alpha comes out with an alpha absolute value to the power p. So why don't we take the expression that we had, and then we just take the p root of that, because then this p will disappear. So the second guess would be to say we take xk, and now the correct definition is coming. So now I will put a p exactly like you see here. I put the number 1, and the way we define it is to be what we had before, the absolute value of xk to the power p But then we take what comes out of this, and then we take the p root of this. This turns out to work. And the theorem tells us that the space LPN, this is actually a Banach space with respect to this norm. So I would like to ask you, do you think this is trivial, or do you see another complication? Now we have defined it such that we know that the second condition is satisfied. Now we know this is satisfied, but what about this one? Is it something that is obvious that this is satisfied with this choice? This is actually far from being obvious. Let me show you how it looked like. There's another theorem in the book, and this is again something that is left to you to prove. This is something you will prove on week 4. So if you look at, there are 2 inequalities on this page, but if you look at this one, the expression you have here, smaller than this, plus this. What does this actually tell us in terms of this norm? Can any of you interpret that inequality in terms of our norms? Yes? This is exactly the triangle inequality, because this, if you look at what this is the norm of the sequence where the kth element is xk plus yk. So what we see here, Minkowski's inequality, what this says is exactly that the norm of xk plus yk, the p norm of this, if you put this into the definition here, you get exactly what is stated here, and you see this is also to the p root. This is exactly what we're working with now, that this is smaller than this term, which is exactly the norm of xk plus the norm of yk. So that means Minkowski's inequality is exactly the triangle inequality for the norm we are speaking about here. So this is by no means trivial to get the triangle inequality for this space. You get it because of Minkowski's inequality, and this is something you'll prove yourself at the problem session in a couple of weeks. So what we'll do now is actually not to speak anymore about Banach spaces. We will move to something that is a little bit more familiar to you, namely linear mappings, linear operators. And then at the end of the lecture, I will give an example of a linear mapping, and this will be in terms of this vector space. So we come back to this at the end of the lectures. So let's look at linear mappings. And this is something you know from most of you from Mathematics 1, or those of you who are coming from elsewhere certainly heard about linear mappings as well. So a linear mapping on a vector space So what does it mean that a map T is linear? This means that if you want to evaluate T at a linear combination of elements in the space, that means we want to evaluate T at some alpha v plus beta w, then this should be exactly the same as just alpha times T evaluated on the v plus beta T evaluated on the w. And this should hold for all linear combinations of elements in the space. So this means this should hold for all v and w belonging to the space. and it should happen for all choices of the alpha and beta. Now, at least in Mathematics 1 at DTU, I know that you are not speaking so much about linear mapping on complex vector spaces. You're dealing with real vector spaces most of the time. So this means in the setting of Mathematics 1 at DTU, you would say alpha and beta belongs to the real numbers. But what we're doing in this course is that we usually speak about complex vector spaces, and this means that in most of the cases, we'll speak about alpha and beta that belong to C. Now, if you think about the notation you usually use in the context of matrices, very often you don't put these parentheses. So that means very often when we speak about linear mappings, we will simply write alpha and then T V without the parentheses and plus beta T W. So this does not mean that we are calculating anything. This just means that what we're doing here is to use a short notation. We simply take away these parentheses. Now, if you remember what you did in linear algebra, when you considered linear mappings, you just used this condition and nothing else, and then you started to speak about linear mappings being represented by matrices, for example. Everything works perfectly in linear algebra, just based on this definition. But there is a big difference between the vector spaces you are using in linear algebra and the vector spaces we are using here. So the vector space Rn, this is a finite dimensional vector space. You know, Rn, you have a basis just consisting of n vectors. Again, Cn, this is also a finite dimensional vector space. This is also n-dimensional. But the spaces we are speaking about now, they are infinite dimensional. You can see it already in the notation here. Up here, you have a finite dimensional space. Down here, you certainly have an infinite dimensional space. So you cannot write down a basis for this space just consisting of 100 elements. You actually need a basis consisting of infinitely many elements. And this means that this definition of linearity, we need that, but this is not enough for us in the study of linear mappings on vector spaces. So there's a technical condition we need in order to work with linear mappings on infinite dimensional vector spaces. So it is a little bit difficult to motivate that definition, but I will just write it down for you. So the technical condition is formulated in the book as definition 241. And what it says is that a linear mapping is bounded. So this is the new word, that it is bounded. So a linear map T, which goes from a vector space V into itself, is bounded. The new word, bounded, if, and what you need to check is that there exists a constant, which is a positive number, such that whenever you calculate the norm of the image TV, then this needs to be smaller than or equal to this number k times the norm of V. And this has to work for all elements in the space. It turns out that this condition is always satisfied when you're looking at a linear map on a finite dimensional space. So that's the reason that you never need to worry about it in linear algebra, because this is satisfied automatically. But in the case of infinite dimensional vector spaces, we need this condition. So what you should do in practice is you just calculate this number, and then you need to check that this is always smaller than or equal to 15, for example, 15 times the norm of V, with a factor k that is the same for all elements in the space. In principle, we don't worry about how big this number is. We just want that such a number exists. However, there are some cases where we would like to know the smallest value of k that we can put in here, and we have a special name for the smallest one you can put in. So the smallest possible value of k, we have a special notation for it. So we denote it by t, and then with the norm bars around the t, and this is called the operator norm of t. So don't worry too much about the naming, that it is called the operator norm on t. This is something that those of you who would like to have functional analysis later, you will find out why this is called the operator norm on t. I will not go into details of that. I'll just say that we are looking at this inequality, and we are searching for numbers k that we can put in here. And in case this definition is satisfied, then if we take the smallest possible value k, then this is called the operator value of t. Now, there's also another small difference between what I'm doing here and what I do in the book. So here on the blackboard, I want to describe the theory as it looks like in most applications, but the book is a little bit more general. So in the book, I look at an operator t going from one space, V1, into another space, V2. So in principle, it does not need to be the same spaces we have here. So in the setting of linear algebra, this could be that you're looking at a linear mapping going from Rn into Rm, for example. So that means this would be a linear map that is described by a matrix, which is not a square matrix. So the setting we're discussing here corresponds to square matrices, and this setting is the one that would correspond to, for example, just a rectangular matrix. So in principle, these spaces could be different. And if you're looking at this, then you need to be a little bit more careful with the notation than I am here, because then when you put in the bars, you always need to write, are we dealing with the norm in V1 or are we dealing with the norm in V2? So for example, if you look at this condition t, v smaller than or equal to k times v, this should hold for all v in the space V1 then. So this means that this measures the element of v in the right space, so therefore we would have to put a 1 here. But t maps V1 into V2, so that means the element we have here is an element in V2, and that means we would have to put a 2 here. So either we write it as 2, or we write it as V2, or here we write it as 1, or we write it as V1. There are different ways of writing that. But at least we need to put some symbols on the norm to tell which one we are speaking about. So I decided to remove this detail because the case I describe here is the one that will appear in most of the exercises. So let's do that on some examples. So what I'll do for the rest of the lecture is to consider 2 examples that are not in the book, where we consider exactly the classes of norm vector spaces we have introduced so far, and then we define some linear mappings. So maybe it's a good idea to keep this. So for the first example, let's go back and look at the continuous functions on an interval. So we will consider an operator t, and it should be defined on the space of continuous functions on the interval 0, 2, and it should map this space into itself. So that means we need to tell, if you give me a function f sitting in this space, I need to tell you what should t of f be. So t of f should again be a function. That means to tell you what t of f is means that I need to tell you what is t f calculated at a point x. And the way I define this is to say this should be x to the power 2 times f of x. So now we have written it down in a very mathematical way, but what really happened here is you give me a function f, any function that is continuous, and then I give you a new function, and this new function is x to the power 2 times f of x. Then what we would like to show and you might think that I just want to show two things. Because from the description I gave you so far, we want to check that it's a linear mapping and we want to check that it is bounded. But I would like to put that as point 2 and 3 because I think there's something we should check before we do that. But let me write this as point 2. We want to check that t is linear. And we also want to check that this technical condition is satisfied. So we also want to check that t is bounded. But as I say, there's one thing I would like to check before we do these two things. So we need some blackboard. So while I make the blackboard ready, try to think about what could it be that I would like to check before I start with this program. So do you have any idea what could be point 1? Yeah, Matthias?
That t actually maps the function into the continuous functions.
Exactly. So what you say, here I claim that our t takes any function sitting here and maps it into here. We did not give you any argument for that, and you're absolutely right that this is something we should do. So the first thing we should do is to show that t is what I will call well-defined. Well-defined means that it actually takes a function in C02 and maps it into C02. So t actually maps C02 into C02. And Matthias, what do you think about that? Is that satisfied here, or do we have a problem?
I'd say that it's satisfied.
You say it is satisfied?
Yeah.
This is great, because if we take any function f, and this is a continuous function on the interval 0, 2, and then we multiply it with x to the power 2, then we get a new function which is continuous and which is defined on the interval 0, 2. So point 1 is satisfied. Because x to the power 2 f of x, this is also a continuous function. On the interval 0, 2, if f is a continuous function on that interval. So you see, in this example, it turns out that there's not so much to prove. It turns out there are many other examples where actually we have to prove something at this point 1. And the good news, and this is something you will not see in this example, but you will see it in the next example I make, very often, if you make a careful analysis at the first point, then you more or less get point 3 without doing extra work for that. But this is something we will see in the next example. So here it actually worked. Could you give me an example where this would break down? So if I make another definition of T, would we have a problem? So if I try to take Tf of x equal to something else, can you give me an example where this would not go? Matthias?
With the definition of the space, wouldn't 1 over x work? 1 over x is
Yes, for example. So if you take 1 divided by x, f of x, this one would give us a problem, because the function is a continuous function on the interval 0, 2, but this function 1 divided by x is not even defined at the point x equal to 1, x equal to 0. That means this function does not belong to the set of continuous functions on the interval 0 up to 2. So here we would have Tf does not belong to C 0, 2. So this was just a remark showing you that it works because of our special definition of the T. Okay, let's prove the linearity then. So linearity means that we need to look at T, and then again, instead of writing alpha v plus beta w, we write alpha f plus beta g, because now we're dealing with functions. So we need to show that this is the same as alpha tf plus beta tg. But this is a function. So to look at this function means that we need to calculate it in some points x. And the value in some point x, this is what we see here. This is x to the power 2. And then we multiply with this function calculated at x. That means we multiply with alpha f of x plus beta g of x. But if you look at this, you can see this is the same as, you can take the alpha out. So this is alpha x to the power 2 f of x plus, and again here for the second term you can take the beta out. So beta x to the power 2 g of x. And if you look at this, this is exactly alpha times, and this is our tf of x plus beta, and then x to the power 2 g of x. This is t g of x. So that means no matter which x you are putting in, t alpha f plus beta g, what we have here, this is the same as the alpha tf of x plus beta tg of x. So since this holds for all x, this just means that t alpha f plus beta g, so the function t alpha f plus beta g, this is the same as the function we have here, meaning alpha tf plus beta tg. So this proves that the function is linear. What about being bounded? So in order to show that it is bounded, then we must find k such that Tf a norm, and then again the norm we have on the space is the infinity norm, so this must be smaller than or equal to k times the norm of f. Do you remember from last week? Yeah, what do you say?
If no norm is defined, do we just choose the infinity norm?
On the space of continuous functions on an interval, you always take that norm. So even if I did not put the infinity, you should understand it that way, if I forgot to write it. Maybe you remember from last week, we also calculated this infinity norm many times, and I say to you, this is too complicated to work with. So TF infinity. If you write down the definition of this, this means that we are looking at the max value for TF of x, where x belongs to AB. This is the definition of the norm of TF. But this is too complicated to work with. So instead of working with this right away, I suggest that you always start to work with what is inside. And then after making an estimate of TF of x, then we can always take the maximum after that. So let's start by looking at TF of x. So this is then, we have to put in the definition of the TF. So this is x to the power 2 f of x. And then x to the power 2 is positive by itself. So this is x to the power 2 times f of x. So what kind of estimates would you like to make on that? Nikki?
This is smaller or equal to the supremum of...
So for this one, you'd say this is smaller than or equal to the supremum. So you'll write this as f and then infinity. What about the x to the power 2? What can we do about that? Yeah, go.
Plug in the maximum value of 2, and then we get 4.
We are looking at x belonging to the interval 0, 2. So that means this is smaller than or equal to 4, and this holds for all x belonging to the interval 0, 2. So this means no matter which x we are looking at, TF of x in absolute value is smaller than or equal to this fixed number. Now we can go in and take the maximum. So we take the maximum over all these values, and all of them are smaller than or equal to 4 times the norm of f. So therefore also the maximum is smaller than or equal to 4 times the norm of f. So this actually concludes the example, but I would like to put in just one more comment. Namely, if you look at the way we define the norm of the operator, then we say, let's just take any value k that works here. Then when we put in the smallest possible value of the k, this is the one that is called t with the 2 bars on the other side. So somehow it is natural to find out what is the relationship between this number and then the operator norm. So what I would like to hear from you is, what is the relationship between t in norm and then the number 4? There's a certain inequality between these numbers. Which way does it turn? Which one is biggest? Yes? You say this is smaller? Correct. And why?
Because since we know that 4 is a number.
4 is a number that satisfies the inequality.
Then there could be a smaller number.
There could be a smaller one, and norm of t is defined to be the smallest one that satisfies the inequality. That's correct. So it turns this way. If some of you want an extra challenge at the exercises, you can actually try to check if the norm of this is equal to 4 or it is smaller than that. But this is a little bit complicated, so this is not something I'll do at the lecture. Okay, this gives you one example. The good thing about bounded linear operators is that after a couple of weeks in Mathematics 4, you'll have seen that you have checked operators being bounded many times. So this is something that turns into a standard question for you. I mean, even though it's an abstract course and there are many things that are complicated and you need to get good ideas in the exercises, there are exercises also that are standard exercises. For example, you saw it already last week, you saw examples of that. To check that, I mean, to find the supremum of a sequence, to find a supremum of a function, this is standard exercises, this is something you'll do many times. To check that something is a vector space or a subspace, this is also a standard exercise. to check that something is a normed vector space, is a standard exercise, and also to check exactly the program we had here. We look at a certain operator, check that it is well-defined, linear, and bounded. This is also an example of a standard exercise. So this is something you'll do again and again during the course, and you'll be very familiar with it at the end. So I hope already the next example I give you, we can just do that before you have to go to the problem session, that this will show you that the program that maybe looked a little bit complicated for you here, that it will already look more familiar with the next example I give you. So the first example was with functions, continuous functions. Now I would like to give an example with sequences. So we take exactly the same formulation as I had here. So again, we consider something, and now it should be, again, at T. Now it should be defined on the space LP, the one that we defined by requiring that this number should be finite. So T is a mapping that goes from LP n into LP n. And the way that we define it is T, and then we should put in a sequence xk, k going from 1 to infinity, and then the outcome should be a new sequence indexed on the natural numbers. And the way I define that is that we put in the sequence xk, and what comes out should be xk plus x with index k plus 1. So it's a little bit difficult from this definition to see what the operator actually does. So let's write it down. So what it means is you put in an infinite sequence of numbers. So you put in some x1, x2, x3, and so on. And what comes out is the sequence given by xk plus 1. So that means for k equal to 1, you see, the first element in the sequence will be x1 plus x2. For the next element, this is when you put k equal to 2, then you get x2 plus x3. And then it continues like this. So you get x3 plus x4, and it goes on like this. And then again, we take the same formulation, so we would like to show. First, we would like to show that T is well-defined. And here, actually, we can see that there is something to prove, because it is by no means obvious that if you put in a sequence belonging to LP, then the sequence that comes out here will also belong to LP. This is not clear. So here, there is certainly something to prove, to show that the operator is well-defined. So T is well-defined. So this means we need to show that T xk, I will not continue to put this k equal to 1 to infinity, you know what I mean. So we will show that this belongs to LP of n if xk belongs to LP of n. And we show, exactly like before, that it's linear and bounded. So let's start with number 1. So again, we must start with what we know. What we know is we take some sequence xk belonging to LP, and then we need to show that txk also belongs to LP. So we have to start with xk belonging to LP. So this is the point where you can be more or less exact. You see, some mathematicians, they would just write down, now we look at t xk. But actually, I'm not very happy about this notation yet, because somehow this notation says that txk already belongs to LP, so we can measure the norm. So somehow, it's a little bit too early to use this symbol. We want to calculate this, but we don't really know whether we have an element in the space yet. So we actually have to look at the definition of the space. So we want to check that this element belongs to LP. So what we really should look at is xk plus xk plus 1 to the power 2 and then we should check that this is finite. And this means we can as well check that it is finite after putting it to the power 1 divided by p. And you see, what I state here is exactly the same as this. The only difference is that this norm symbol, we only put it after we have shown that this is finite. So at the end of the day, when we have shown that this is finite, then we can use this symbol. But so far, where we don't know it's finite, we actually have not defined this in a strict sense yet. But some people, they allow themselves to be a little bit sloppy, and they write this down anyway, and then at the end just show that this is finite. I put it in parentheses, because I think the most exact way is just to calculate this and to show that this is finite. So how can we show that this is finite? Actually, you only have one trick that you can use. So here you have a sum of the absolute value of 2 elements. And the only trick you can use is actually the Minkowski inequality that I showed you before the break. Or it was just at the beginning of the lecture, I think. So you see, we have it here. It's the one that says that if you look at the sum of the absolute value of some xk plus yk to the power p, and then you take the peak root, then this can be estimated with something that has to do with the xk alone and something that has to do with the yk alone. So if you use that inequality on the expression we have here, then you can see the xk is the same as the xk over there, and the yk over there is the same as the xk plus 1 here. So if you simply take the Minkowski inequality, then we see that the expression we are looking at is smaller than or equal to the sum of xk to the power p, k going from 1 to infinity, and then we take the peak root of that. This is the first expression, and then over there you can see we get exactly the same expression with respect to yk, and the yk is now the xk plus 1. So we get the sum of xk plus 1 in absolute value to the power p, and then we get the peak root of that, and we get the sum from k equal to 1 to infinity. So what is this? Let's just keep the first term. So this is still the sum from k equal to 1 to infinity, xk to the power p to the power 1 divided by p. But we can also do some manipulations on the second term, because you can see this is, here we have xk plus 1 summing from k equals 1 to infinity. But this is just the same as the sum of xk to the power p. Now, where we change the index, such that instead of going from k equal to 1, we go from k equal to 2 to infinity. And now you can see, here we are making the sum from k equal to 1 to infinity. Here we make the sum from k equal to 2 to infinity. So this is certainly smaller than or equal to if you just add an extra term, if you just add the term corresponding to k equal to 1 here. Then if you do that, then this term will be exactly the same as the term we have here. So everything can be estimated by just 2 times the sum k equal to 1 to infinity, xk to the power p, and then the pth root of that. And our assumption is exactly that xk belongs to the space LP. So that means we know that this is finite. So this is finite because xk belongs to LP n. So what we actually have shown now is that whenever we take a sequence xk that belongs to LP and we put it into our operator t, then we get something out which, measured in our p-norm, turns out to be finite. So this means we have shown that t applied to xk actually belongs to LPn. And this is what we wanted to prove. So this was a quite complicated and long proof just to show that the operator is well defined. But there's something good to say about this, and I'll come back to that in just a minute. Now, the linearity. This is something I will leave to you to prove. I mean, that you put in a sequence like this, and what's come out is x1 plus x2, x2 plus x3, and so on. That this is linear. This is something you can prove exactly like you prove linearity in Mathematics 1. So there's nothing new in that part. So linearity, this is something I leave to you. But point 3, we need some more space, but please tell me how much work do we need in order to prove point 3? So how much do we need to do? What's your name?
Søren.
Søren. Okay.
Yeah, we have already shown that it's smaller than or equal to 2 times the norm of xk.
So what you say is we have already shown that this expression, which was the same as t applied to xk, measured in p-norm, that this is smaller than or equal to this. So this is completely correct. So let me just mark it. So we calculated this, and we did a lot of estimates, and we showed that this is smaller than or equal to 2 times this expression, and this expression is exactly the norm of our sequence. So this means the argument we did in the first part it shows that the norm of t of the sequence, and again I skip all these k going from 1 to infinity, that this is smaller than or equal to 2 times the norm of the sequence for all xk belonging to LP of n. So what this says is that t is bounded, And again, we can say something about the relationship between this number 2 and the norm of the operator. So we also get that the norm of t is smaller than or equal to 2 because we can put in the number 2, but potentially we could put in something smaller, and the smallest value that could be put in here is the one we denote by this. So this actually completes the proof that we have a bounded operator. And the good news, and I think I will write it down because this is really something that is useful for you. So the good news here is that, like we did here, a careful proof of the first part very often gives the third part, the part with boundedness, for free, exactly like we saw here. You can see you need to be a little bit careful with the wording here because I say very often, because we just had an example 1 where we didn't get it for free. But actually, what you saw in this example 2 is what you will see in, I'll say, almost all the exercises that you'll meet at the problem session. So this is very typical that this happens. You had enough for today. Before you go, I would like to hear how many of you know about proof by induction. If you could raise your hand. Maybe it's easier to ask how many of you don't know about proof by induction. Okay, if there are a few of you who don't know about proof by induction, you're welcome to come down and just speak to me now, because then I'll give a very short introduction to that. And the rest of you, please just go and do the problem session. We'll meet there.